We already learned about standing waves set up in strings and springs. Today we're going to learn about standing waves set up in air columns and find out how all of this relates to the sounds that we hear when a musical instrument is played. We saw for standing waves set up in strings, or in this case, a spring, random frequencies didn't set up standing waves, and yet when we hit just the right frequency, we could establish the fundamental frequency, the first harmonic. When we vibrated twice as quickly, we could set up the second harmonic that looked like this. And when we vibrated the spring 3 times as quickly, we found the third harmonic. Let's look at a different type of standing wave. I have a bottle of air here, right? I'm going to blow across the top of the bottle. And when I did that, I actually set up a whole bunch of frequencies of vibration of the air above the top of the bottle. We call it turbulence. But you only heard one tone, one frequency. And that's because that sound wave came down into the bottle, reflected off of a very rigid or fixed end, so it inverted, reflected, and then the incoming waves interfered with the reflected waves, just like on the string that we looked at before. But most frequencies did that and interfered randomly and chaotically. But that one frequency you heard fit the air column just right, so it set up standing waves. And so the vibrations got extra big, like on the Tacoma Narrows Bridge, and that resulted in a very loud sound, and that was the tone you heard. Let's look at what those standing waves must look like. This is a representation of the longitudinal sound wave, represented as a transverse wave for simplicity. This end of the simulation of the wave would represent the bottom end of the bottle because it's a fixed end, so the waves reflect and invert upon reflection, so we always get destructive interference that forms a node. The top end would be a free end because the air molecules are very free to vibrate there. And that's represented at this end of the wave where we have an antinode. And so this is the standing wave that is set up. Now, if you want to look at the two waves that were creating that, the blue wave is the reflected wave. As you can see, it's moving left to right. The orange wave was the incoming wave. You can see it's moving right to left. And you see at this end, we always get destructive interference because the orange and the blue are in opposite positions. And at this end, we always get constructive interference because they are always in the same position, constructive interference. So with this pipe, you can hear the fundamental, but you can also hear a second harmonic. So let's take a look at what that looks like. On this simulation, you can see that the second harmonic is formed with the same length of air column, and we have a node at the bottom at the closed end again because we have the wave interfering with its exact opposite, the inverted reflection. But we also have another node, and we still have an antinode at that free end. Here's what it looks like in motion. The third harmonic looks like this. So you can see that each time we're adding a loop, so to speak, an antinode into the pattern and keeping the same length of the medium. So here's the mathematics behind that. The length of the pipe stays the same. For that fundamental, that lowest frequency, we fit 1/4 of a wavelength into the pipe. This next harmonic that we get is 3 times the fundamental because you see that we fit 3/4 of a wavelength, and then 5/4 and 7/4. So the interesting new pattern we have is that the harmonics are formed at the fundamental, 3 times the fundamental, 5 times the fundamental, and 7 times the fundamental frequency, a different pattern from what we had before. Let's look at a different type of standing wave in an air column. This pipe is open at both ends. It's a straw. So when I set up turbulence, sound waves go in, reflect off a free end, and interfere with the incoming waves, and you hear the one frequency that sets up standing waves in this length pipe. Notice with a longer pipe, a lower frequency, lower pitch, lower frequency wave interferes constructively, and that makes sense because a lower frequency would have a longer wavelength, and a longer wavelength would fit in a longer pipe. So let's look at what those standing waves look like. Here's what the standing waves in an open pipe look like. The pipe is open at both ends, and so there's an antinode at both ends because both ends are free to vibrate. So the first possibility is that we have a half of a wavelength fitting into the pipe, and that would be our fundamental frequency. In order to fit in one more antinode, we would have a waveform that looks like this. And notice that we have crest, trough, crest, a full wavelength fitting in, so we have a familiar pattern of frequencies to developing the harmonics. A fundamental, twice that, 3 times that, and 4 times that. Very similar to a string that's fixed at both ends. When you hear the term harmonic, maybe it makes you think of music. So let's see how this relates to music. In this case, we're going to look at the music form produced by a guitar. And what I'm going to do is I'm going to set up standing waves in the string. When you hear this tone, when I pluck the string, you're hearing the string vibrating in its fundamental frequency. I'm going to force a node halfway along the string. I've measured it before, and I want you to listen to the second harmonic. First harmonic, second harmonic. Here's the third harmonic. Different. And here's the fourth harmonic, setting a quarter of the string into vibration. So listen again to the first, the second, and the fourth harmonics. Those of you who have any experience at all with musical instruments will recognize those as octaves. In order to get from one octave to the next on the musical scale, you double the frequency. And because of the pattern that we saw with standing waves in a string, where the harmonics were at the fundamental and twice that, 3 times that, and 4 times that, the first and second and fourth our harmonics are octave jumps. The next octave jump would be at the 8th harmonic, quite a ways up from those first ones. So a little tie-in to music along with this idea of standing waves.